Okay guys, so this is now time for models, lots of models. So the first model that we're going to begin with, other than our geometric model, is we're going to establish a very simple random variable. We want to have a random variable whose values x are going to be just 0 and 1. Now, if you like, you can think it about flipping a coin or drawing a heart from your deck of cards. And so, in general, we can say x as being a success. We'll call the number 1. So that's the affiliation between this description and the value. And so, x being a failure can be associated with the number 0. Now, we need probabilities associated with these, but for example, if we're flipping a coin, you would probably say a head is success, could, and then p of 1 would be a half. But if you're drawing a heart from a deck of cards, then the probability of success will be 1/4, because there's only 1/4 of the cards are hearts. So we're going to associate with p of x equal to 1 the number p, and p will be less than or equal to 1 and greater than or equal to 0. Now, it won't make sense to set it equal to 1. It won't make sense to set it equal to 0. That means the other one is completely taking over. So we're going to do non-equals here. And then that means the complement will be q, and p plus q equals 1. Now, this is nothing more than a mathematical definition of flipping a coin, drawing a card, and has an associated probability, and this is called Bernoulli. Now, the most important thing about the Bernoulli distribution is that it's just a single event. So let's look at the characteristic. So characteristic is a single event. It has 2 values only. Should be easy to spot when you have a Bernoulli. You do something once. Now, let's look at the theoretical expectation. Well, 0 times q plus 1 times p, and so the expectation will be p. Not bad. Let's do the variance, the expectation of x squared minus mu squared. So the expectation of x squared will be the sum over x equals 0 to 1 of x squared p of x, and so this will be 0 squared times q plus 1 squared times p. It will be p. So I think I made a mistake there. Oh, yeah, I'm not done. So sigma squared then will be p minus p squared, which will be p times 1 minus p, which will be pq. And so sigma will be the square root of pq. A pretty simple calculation, theoretical. It's just what happens when you're flipping a coin that has some associated probability. Okay. Now, what's neat about the Bernoulli is that one would think that it would be trivial and obvious to apply. And the answer is, well, yeah, but normally we do repetitive Bernoullis. So normally we do something like this. Now, let me associate a real-life situation with this. Let's suppose that p equals 1/2, q equals 1/2, and p is associated with having a girl, and Q is associated with having a boy. So this here says it's two girls. This here says a girl followed by a boy. This here says it's a boy followed by a girl. And this here says it's a boy followed by a boy. So the Bernoulli is just telling us that there's a 1/4 chance of having two girls, a 1/4 chance of a girl followed by a boy, a 1/4 chance of a boy followed by a girl, and a 1/4 chance of a boy followed by a boy, just multiplying the probabilities. But using this Bernoulli, we can ask a question like, what's the probability a family of two children is 50-50? Well, that's going to be a half. It'll be the sum of these two probabilities. So we use the Bernoulli in independent sequential trials to do calculations. Now, why is the first trial and the second trial of this Bernoulli independent? Well, when you flip a coin, can the future coin know what happened in the past? And the answer is no. So sequential Bernoullis have this potential of creating some very interesting situations. Well, let's run this a little bit further. Let's go to three girls, two girls followed by a boy, girl, boy, girl, girl, boy, 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 girl, left is girl, boy, girl, girl, boy, boy, girl, and boy, boy, boy. 8 possibilities, and this is a 1/8, 1/8, 1/8, 1/8, 1/8, 1/8, 1/8, 1/8. But now if we don't worry about the order in which this is happening, just like here we said a probability of 2 kids in a family, we can ask the following question. What's the probability of the number of girls in a 3-child family equals 3? Well, that would be 1/8. How about the probability of the number of girls in a 3-child family equals 2? Well, here's 2 girls, here's 2 girls, here's 2 girls, here's 2 girls. That's 1/8, 1/8, 1/8, 1/8. That's why do I feel uncomfortable? Girl, girl, boy, girl, boy, girl, boy, girl, girl. Oh, these two are the same. That's why I feel uncomfortable with it. That was a boy, girl, girl. This is a boy, girl, boy. All right, so probability of girls in a 3-child family is 2 is 1, 2, 3 eighths. 1/8 plus 1/8. Now the probability that the number of girls in a 3-child family equals 1, well, that's 1 there, 1 there, 1 there, and that's 3/8. And then the probability of the number of girls in a 3-child family equals 0 is 1/8. That's this one. I want you to notice that the numbers we've seen here and here relate to the binomial tree. We have a 1, a 1, 1, a 1, 2, 1, a 1, 3, 3, 1. And that's that probability, this equitable probability being multiplied out. Now, I didn't do this very generally. I said P equal to a half, Q equals a half. So let me repeat that with it being a little bit more general. So here's a P and a Q. Here's a P, so this is P squared. This is PQ. This is QP. This is Q squared. I'm putting the probabilities in, so now this will be P cubed, P squared Q. This will be QP, P Q squared. This will be QP squared, followed by QP Q, and this will be Q squared P, followed by Q cubed. Now, I wrote the probabilities at the location, and it's also keeping track if you've had success or failures. My previous example, the girls were a success. I'm going to make boys a success. No, it doesn't matter. I just want you to notice that 2 p's are here, here, and here. There are 3 p squared q's. 2 q's, they are here, here, and here. There are 3 pq squareds. P cubed, there's 1 p cubed. Q cubed, there's 1 q cubed. In other words, we have 1 p cubed plus 3 p squared q plus 3 pq squared plus 1 q cubed, which is exactly what this row of the binomial tree says. That's p plus q cubed. That is the 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. That is indeed what the binomial tree calculates. So if we just want to count the occurrences of something, unorder the births, not say girl, boy, girl, but simply say 2 girls. If we unorder the repeated Bernoulli, we get what we call the binomial distribution. And x equals a count. We have to know how many trials we do. So are we going to do it n or k times? We'll do it n. So x is the count, and we'll say of success, but we associate it with the number p. That's it. The probability that that specific success is p. And then what is the calculation then? Why, it's nothing more than n choose x times p to the x q to the n minus x. That's what that calculation is. So let's just do one here. Let's set n equal to 3 and do the probability that x equals 2. Well, 3 choose 2 is 3. P squared, q to the first, and that was indeed what we got there. This binomial distribution is really neat, and it just counts the occurrence of repetitive Bernoulli experiments. Now, it turns out that when you graph the binomial distribution, it isn't exactly symmetric, because if p is not q, there's going to be an anti-symmetry to the probability mass function histogram. Because we will have, for example, 3p squared q will be probably greater than 3pq squared if p is bigger than q. But the other way around, it would be higher. So what happens is that these distributions have a habit of having asymmetry to them. Well, given this asymmetry here, then it would be very, very reasonable to be able to calculate these quickly and easily. And in the back of the book, we have something called the cumulative probability function. The cumulative probability function we call f of x, which is, by the way, intentionally used capital F because it's associated later when we get to continuous ones. It's associated to integration. It is going to be the sum of all of the x's in the sample space where they have a very specific role. For example, the x less than or equal to k. Oops, sorry, I said that completely wrong. Let's start again. The cumulative probability up to a value x will be the sums of the x's in the sample space where that x is less than or equal to the little x given the probability of x. Here's where we're writing it in a kind of an odd way. It's also written the probability that the random variable is less than or equal to x. So up here, it looks like I have a 0, 1, 2, 3, 4 as a count. And so this is a n equals 4 picture. And if I was interested in f of 3, then in this picture, it would be the sum of those three values. So you sum from one point up. Now what's nice about this is that suppose you calculated f of 4 minus f of 3 with a calculator. Look in the back of the book. Well, this will be equal to your f at 4 because it'll take all of this minus that. If you want f of 2 using a cumulative, you can do f of 2 minus f of 1, and that will be little f of 2. So the cumulative at a point, when you subtract the point to the left of it, will give you a probability that you like. So this picture here is this value minus this value is just that one bar. So the cumulative distribution contains the information of the probability mass function. So that makes it a nice thing to know about and to work with. Now what's interesting about these cumulative probability distributions is that because you're adding up probabilities, these things are getting higher, higher, and higher. And when you finally reach, so you start down here at 0 and you increase until you reach 1 because you're adding up all of the probability values. This is what pretty much every cumulative distribution will look like, an increasing bar graph that contains values. Now, sometimes we're interested in ranges of values. So what if I want the probability that our random variable for some distribution is less than or equal to 12, but greater than 6? Well, first I would make it into a very clear statement, if you like. But then you can notice, well, everything from 6 down has been thrown away, so you could easily say, oh, this will be the f of 12 minus the f of 6. And so again, even ranges of values can be calculated with the cumulative distribution rather quickly. What happens if we play with things and we do greater than or less than? Well, you just have to spot if you want this answer, that's a greater than question, well, just take 1 minus this answer. So a typical question is, suppose you want probability of x greater than or equal to some number k. Well, that'll be 1 minus the probability that x is less than k. But less than in a discrete will be 1 minus probability of x less than or equal to k minus 1. And now you can use the cumulative function on k minus 1. So what's really nice about these things is that the cumulative function allows us to do calculations, some of them very quick and easy. Well, now that we've got this new distribution called the binomial distribution, first thing we want to do with that is calculate mu for binomial distribution. So I want you to think if you were flipping a coin, 0 was a tail and 1 is associated with a head. If over a long period of time you'd expect about the same number of heads and tails, you'd like to see the expectation equal to a half. But what happens if it was more like drawing one card from a deck of cards exactly once? What's the probability of getting a heart? Well, to get a heart, that might be associated with a value of 1/4. And not a heart, 3/4. Now if you do this repetitively over and over and over, what's going to be your average value if 1 means heart and 0 means not heart, and how would you interpret it? So let's first off take a look at mu here for the binomial distribution. By definition, mu is the sum of x's in the sample that this works on. X times n choose x, p to the x, q to the n minus x. Now, because n has been given in this problem, that is the largest count possible, we know that this sum starts at 0 and goes to n, x, n choose x, p to the x, q to the n minus x. Now, a lot of you probably don't necessarily like seeing n, p, q, and x in one problem, and you're just concerned, what in the world am I going to do with this kind of crazy equation? Well, the answer is maybe we should just ask ourselves what it looks like if we put in a couple values of x. That's not a bad idea. Help us understand it. So I'm going to do that. If I put in 0, I get 0. If I put in 1, I get n choose 1, p to the first, q to the n minus 1. And then if I put in 2, I'll get 2 times n choose 2, p squared q to the n minus 2 plus 3 times n choose 2p cubed q to the n minus 3. Oh, this is n choose 3. Sorry. Well, one thing I can do is I can observe, heck, I don't need that 0 term, so I'll throw that away. So this is a sum from x equals 1 to n of n choose x times x, p to the x, q to the n minus x. Don't know if that really helps, but, you know, it's not a bad thing to observe. Maybe I should write these out. That seems kind of silly to not have tried that. So let's just write them out. Again, I'm going to try to write it out. That 0 didn't seem to help me so much. But I'm going to start at 1. n choose 1 is n factorial over 1 factorial, n minus 1 factorial, p to the first, q to the n minus 1, plus the next one is 2 times n factorial over 2 factorial, n minus 2 factorial, p squared, q to the n minus 2, plus 3 times n factorial over 3 factorial, n minus 3 factorial, p to the third, q to the n minus 3. And I start noticing that that x in top, I can cancel with one of the factorials. There's a 1 here, 2 here, 3 here. Seems pretty clear that the n of n choose x is n factorial x factorial n minus x factorial. With an x in the top, this is reducible, namely to n factorial over x minus 1 factorial n minus x factorial. That seems like a very reasonable simplification. Well, now we're going to do a tricky math substitution. We're going to change the variable of x. We're going to make it a different variable. And in so doing, I'm going to rewrite my sum in a different way. So in order to accomplish that, I first want to note that this really does look like somebody's doing some sort of binomial calculation. It's just that the binomial calculation is not exactly what I expect it to be. So I'm going to force this to look a little bit more binomial. How am I going to do that? I'm going to say let k equal x minus 1. Okay? If I do that, then every term that I've been simplifying here looks a little bit different. We still have the n factorial in the top. I now have a k factorial in the bottom, and n minus x well, x is k plus 1, so n minus k plus 1 will be n minus x, so that'll be n minus k minus 1 factorial. P to the k, is that a p to the, yep. No, that's going to be a p to the k plus 1, q to the n minus k minus 1. So that's what each of these terms looks like. Now, this looks good. This almost looks like a binomial. If I could just make this read n minus 1 minus k, then it looks like an m factorial, m minus 1. So I'm now going to do the following. I'm going to take that expression that we have, n factorial over k factorial, n minus 1 minus k factorial, p to the k plus 1, q to the n minus 1 minus k, and I'm going to pull out an n up here and pull out a p. So now I have n minus 1 factorial, I have a k factorial, I have an n minus 1 minus k factorial, I have a p to the k, q to the n minus 1 minus k, and now I'm going to let m equal n minus 1, and I'm going to have np, and it'll be m factorial over k factorial, m minus k factorial, p to the k, q to the m minus k. Each and every one of these terms is a different binomial term. And so when I sum this up, the sum ends up here, I am now summing up over a different binomial expression. And that binomial expression is known to add up to p plus q to the n minus 1. But p plus q is 1. So this is np. And we've just discovered that the expectation of the binomial is np. Well, that's really neat. It says that through enough selective and perfectly done math, we can determine theoretically some of these values. So we now have the binomial. It's associated with a p and a q, where p plus q equals 1. It's associated with repeated Bernoulli. We know the expectation is np. In the book, they have the variance, and the variance for the Bernoulli binomial really works out well, npq. So it's a very nice system, this one. All right, so what can we do with this? Well, what we can do is we can ask questions all about when we do repetitive random experiments, where each experiment has the same probability of success or failure, and we repeat them, and we just want to count the number of successes. So, let's take a bunch of popcorn. Let's take n equals 150 popcorn shells. It's known that when we heat them, they pop. It's associated with 99% of the time. So P equals 0.99. So now we pop our popcorn. What's the probability that we have everything popped? What's the probability that we have 5 kernels popped, unpopped? We can now look at counting how many kernels or how many pop shells we have. Well, with this scenario, do you think one kernel popping is independent from the other one? Do they know each other? No. So it seems like a repeated Bernoulli. If it pops, 99%. Not 1/100. So, what's our expectation in popping this bag of kernels? Well, so the expectation is NP, which is 150 times 0.99, which is 150 times 99 over 100. It's 1.5 times 99. So that's 99 plus, well, half of 99. Is it going to be 50 of 49 and a half? Well, we'll put 49 and a half. So we get 148.5. So, how many kernels do you expect to find popped? Well, it looks like 148. 149, very reasonable. This looks like a great bag of popcorn. It has very few kernels in it. This is a way to express things that are happening. Now, I could also ask, what is the probability of 8 unpopped kernels? Well, that's the probability of 142 popped kernels. Well, that's simply 150, choose 142 times 0.99 to the 142nd times 0.01 to the 8. And there we can calculate that probability. Now, I don't like doing those numbers. I like looking them up. But I want to follow this up with another question. What's the probability that we have at least 8 unpopped kernels? What are we going to do with that one? Well, at least 8 unpopped. Well, how about that? The probability of at most 142 popped. So that means it could be 1 popped, 2 popped, 3 popped, all the way up to 142 popped. This is f of 142 with p equal to 0.99. So it looks like it'd be useful to have a table or a formula that does these. They're online, they're in the back of the book. We look these up. We don't calculate them. Some of them we'll learn how to calculate. We'll come up with formulas. But for the asymmetric binomial ones, no. It's something we just calculate or describe. All right, well, there's that one.